Okay, today, this is Physics 1Z for March 30th. Today we're going to be talking about DC circuits. DC stands for direct current. Uh, we're going to be looking at what happens when you take resistors and you combine them together in like series combinations, parallel combinations, just like we did with capacitors. We're then going to learn about Kirchhoff's rules, I'm not sure how to pronounce that, which are rules that you can use for circuits to simplify and understand what's happening in them. Really powerful. They really make solving some of these problems very formulaic and easy, actually, as you will see as we go through. And then the final thing we'll talk about is, I guess this is our first like combination circuit, RC circuit, which is a combination of a resistor and a capacitor. So let's get going. Okay, so just to refresh what we did last week, we were talking about what electric current is, right? And we said that you could say that electric current is like the flow of charge within a circuit, and we said that it's related to kind of the time rate of change of charge flow. We also learned about Ohm's law, which we'll be using today, which is that the potential difference or the voltage in the circuit is related to the current flowing and the resistance in the circuit. And we learned some other things like how to calculate resistance, such as this equation, where if you have a resistor that has a length L, a cross-sectional area A, and a resistivity rho, which is something you look up in a table, you can calculate the resistance of that piece of metal by using that formula. So today we're going to talk about what happens when we take these things called resistors and connect them in series and parallel. We'll do series first. Okay, so for resistors in series, we're going to set up a circuit where we have one resistor right here. This little squiggly line is the symbol you're going to see not only in this book, but in a lot of places for resistors. So we have one resistor that I'll say has a resistance of R1 connected in series, so basically just back to back with another resistor here that we'll call R sub 2. And we'll connect those up to a battery or some type of voltage source. This is the positive side, this is the negative side. That means that within the circuit there's going to be current flowing, and the current flow is going to go like this. Let me get to where I can actually see your questions and stuff. That's the current flow, like that right there. It'll flow up and through both of our resistors here. Now let's talk back to what we did when we looked at capacitors in series to help us understand what we're going to do next here. So we had capacitors that were in series like this, connected up to a battery. What did we say was similar about all of the capacitors that are connected in series?
The charge on them is the same.
The charge on them is the same, okay. Now, resistors don't become charged. They allow current to flow through, unlike a capacitor, which acts basically like a short circuit and prevents the flow of current. So that's why we never talked about current in circuits that only had capacitors. But now, we can think about what happens in either one of these capacitors. When we say that there's current flowing in the system, that means that there are little tiny charge carriers that are flowing around the circuit. So, for example, if we pretend that the charge carriers in our circuit are positive, then we can imagine a charge coming up this direction, going through here, passing through this resistor, and then coming out the other side right here. And for every charge that flows in the left side of the resistor, it also has to flow out the right side of the resistor. The resistor can't somehow absorb the charge, right? The charge can't really escape the system very freely. So, what we say is that any charge that flows in also has to flow out, and that implies that the current flowing through this resistor is going to be the same as the current flowing through the other resistor, because that same little charge is going to eventually have to make its way over to here and continue back through the circuit like this. So we basically say that for resistors in series, each resistor is going to have the same current. So same current through each resistor. If this wasn't true, then you'd have problems with charge conservation. We know that electrical charge is a conserved quantity, and if there was, let's say, more current flowing through R1 than there was through R2, then you could reasonably ask, well, what happened to the current when it moved from R1 to R2? So in order to have charge be conserved, you have to have the current be able to basically be the same in both of them. That wasn't the best explanation I've given of that. Does that make sense to you all? Does anyone have any questions about that? As to why that would be true?
Can you say that again?
Yeah, the basic idea is that, like, if charge is flowing through here, and it's flowing around and around, you can't have charge just kind of build up somewhere in the circuit. It has to keep going. So any charge that flows in the left side of R1 has to flow out the right side, and any charge that comes out the right side of R1 basically has to go into R2 and then flow out the other side as well. So if they didn't have the same current, let's say the current through this one was like, let's say 10 amps, 10 coulombs per second passed through R1, and then I tell you somehow the current here is 5 amps, you'd be like, well, where'd the other 5 coulombs go? You know, every second, 10 amps means every second there's 10 coulombs that pass through this, right? If then I tell you that only 5 coulombs pass through the other one, you'd be like, well, where'd the other 5 coulombs go? Right? Does that make more sense?
Yep.
Okay. So that's not possible, and if this one has 10 amps flowing through it, then you must have 10 amps flowing through the other one too. Now, if somehow in the circuit these resistors could kind of like absorb electrical charges from the atmosphere or something like that, or if electrical charges could escape the system, this might not be true. But that just doesn't happen. The charges tend to be confined within the wires. So we know that we have the same current passing through each resistor, okay? The other thing we know from our discussion of capacitors and the way they work in series is that if the potential difference across this battery is delta V1, then the potential difference across R1 is delta V1, and the potential difference across R2 is delta V2. So if we give them these numbers, what we know is that the total potential difference in the circuit, or the total voltage, should be equal to delta V1 plus delta V2. And the size of the voltages on these is going to depend upon their resistances. So if this is 9 volts, for example, if we just pick a value and say this is 9 volts, then maybe this one is 6 volts and this one's 3 volts. Or maybe this one's 4 volts and this one's 5 volts, but they have to add up together to be 9 volts. The next thing we can do is we can use this equation. And what we'd really like to do is to do exactly what we did in the case of our capacitor circuit, which is we want to reduce this down to a simpler circuit that only has one resistor, like this. So same battery, but now we want to reduce it down to an equivalent resistance that we call R sub EQ that's basically related to these two over here. And so in order to do that and understand what the value of this REQ might be, what we need to do is to replace delta V1 here with the current flowing through that resistor, which is I, multiplied by R1, plus for delta V2, it'll be the current I multiplied by R2. And on the left-hand side over here, what we'll do is we'll say, well, once we've reduced the circuit down, and I have the same current I flowing into my equivalent resistor, which is a combo of these two, then on the left-hand side, well, maybe you all can tell me, what should I put on the left-hand side over here?
IR equivalent.
Yeah, that's right. So this potential difference, delta V over here, from this picture, has to be equal to, well, Ohm's law, I times REQ, exactly as Cam just said. And then kind of similar to the way this worked with capacitors, all the I's cancel out, and we end up getting that the equivalent resistance of two resistors that are in series ends up being the sum of those resistors. And this kind of should make some kind of sense, especially if you think about this equation right here. You know, if I have two resistors in series, you could imagine that if you ask, well, how are these resistors constructed? You could be like, well, the first one's made of metal and it has a certain resistivity and a certain length and a certain cross-sectional area, right? And then right next to it, if I put another piece of metal that has its own resistivity, length, and area, well, then you're just adding up additional resistance to the circuit, right? You're just adding up more constraints to the flow of electricity. So it makes sense that if you put them in series, that it really should just add to the total resistance. Now, if we had, this would be for 2, obviously, right? And you can guess pretty easily that the general equation then is that when you have things in series, you're just going to add up all of your resistors, and that'll give you your equivalent resistance. Just as a comparison, when we did this with capacitors, this isn't quite how we did it. For capacitors, because, just to remind you, for a capacitor, delta V was equal to the charge on the capacitor divided by C, right? Like you compare these two equations here. So you have R to the first power and you have C to the negative 1 power down here. For capacitors in series, what we found was that the equivalent capacitance was basically you take 1 over C1 plus 1 over C2 plus ... So it's kind of reversed. But it should be kind of clear why it's reversed. It's just because the way we define capacitance is kind of inverse to the way we define resistance. All right. And also, capacitance is how much something can hold versus resistance is like impedance to the flow of current. Okay, that's resistors in series, and we'll do a problem here in a second with this, but we're going to talk about parallel capacitors. Sorry, this is resistors in series. We'll talk about parallel resistors next. Anyone have any questions? All right. Okay, so for resistors in parallel, we just draw a circuit where we put one resistor up here, R1. We stack another resistor below it, R2, and kind of like a ladder pattern. And then we have a battery down here. The battery will have a potential difference that we call delta V. Now, because the system is in parallel now, things are going to get a little bit different. Now that there's a junction here at this point, the current that flows in here, which we might call something like I, is actually going to split in two. Some of the current will flow upwards, that we're going to call I1. That's going to be the current that flows up here, back here, over to here. That's going to be the current flowing through that branch of the circuit. And then we'll say that this same current at this point breaks into another current that we call I2 that's going to be flowing through just this branch right here. And then the cool thing about stuff like this is that if you look at this junction and you look at this junction over here, on the left-hand side you've got current I flowing in and it gets split up into I1 and I2. But on the right-hand side, that same I1 and I2 come back together, so they must then come back together to become the same current I. If the current I is equal to I1 plus I2, then I1 plus I2 also is equal to I. You're just kind of reversing the way you're doing the addition there. Also, what do we know about things that are in parallel in terms of their potential difference across R1 and R2 here compared to the battery?
The potentials are equal.
Mm-hmm. So the potential difference on R2 is going to be delta V. Potential difference on R1 is also going to be delta V. Now, as I write those in there, it starts to make this look really messy, so I'm going to try to write them with a different color. So this one's going to have delta V. This one's going to have delta V. You know what? You know what I could do, actually? I could just write over here on the side. Okay. Because they're in parallel, they get the same potential difference across each. Okay. So in order to do this result, I believe what we're going to be doing is saying that, once again, we want to reduce this down to one circuit that has an equivalent resistance that we call Req. And our goal, of course, is to figure out what Req is. you might be able to guess that since with resistors in series you added them directly like this, but with capacitors in series you did this inverse thing. Whereas with capacitors in parallel you added them like this, right? Do you all remember that? So with resistors, we kind of would probably expect that for resistors in parallel you're going to get something like this, right? Does that seem reasonable? All right, so let's see if that happens. So we could start this in a couple different ways. So first of all, we're going to call the current flowing in this region of the circuit to be I. REQ is combining together those two, so the current coming out of our battery here is still going to be I. And what we can do is we can write an equation where we basically say that the current that flows into that junction has to not equally, but has to split up in some way into I1 and I2, dependent upon how much resistance you have in each of those circuits. Probably, well, you all can tell me, if I tell you that the current here is 10 amps, okay, and I have two different resistors here, but I tell you, for example, that R1 is less than R2, let's say. Which of these two resistors do you think is going to have more current flowing through it? It's going to be a portion of this 10 amps, but which one is going to have more?
R1.
R1, yeah. And why is that?
Because there's less impedance to current flowing.
Yeah, exactly. That's right. Okay. So you're going to get more current through the branch that has less resistance. Effectively, the current's going to follow the path of least resistance. So our current I, from our equation on the right over, from our picture on the right over here, should be equal to delta V divided by REQ. I1 should be delta V divided by R1. And I2 should be delta V divided by R2. And then we get our equation. Cancel all the delta V's out, and you get that REQ is equal to 1 over R1 plus 1 over R2 to the negative 1 power. And of course, if you have more resistors in parallel, you just keep adding the inverses. Just like capacitors in series. And there we go. That's resistors in parallel and resistors in series. Really quite simple. Does anyone have any questions? Okay, if not, then we will do a short problem before we talk about Kirchhoff's rules. Okay, so we have a simple circuit here where we have an EMF of 18 volts for this battery. It has an internal resistance of 0, so it's kind of like a perfect EMF source. It's connected up to a 4 ohm resistor, a 6 ohm resistor, and a 3 ohm resistor. And our goal is to reduce this down. It says to find the equivalent resistance of the network and also find the current in each resistor. Okay. So what we want to do is we want to reduce this circuit down into a simpler circuit. The first thing that we can do, maybe I should have asked you all, because you can probably figure it out. What's the first thing that we should do here to start reducing this circuit? And our goal is to make all three of these into one resistor.
Could we add the 6 ohm and the 3 ohm resistor together because they're in parallel?
Yeah, these are in parallel. So to combine those two, what's going to happen is, well, we're going to still have our battery. I shouldn't keep saying battery. It could be any voltage source. We're still going to have the 4 ohm right here. These two are going to reduce down to something. And what they'll reduce down to, we're going to get from doing 1 over 6 plus 1 over 3 raised to the negative 1 power, and the answer is going to give us ohms. 1 over 3 is like 2 over 6, plus this is 3 over 6. You invert it, you get 6 over 3, which is 2. So this one's 2 ohms. And then we can reduce these two down because they're in series. This is a really, really simple problem. So 4 and 2, we just add them together because they're in series, and you get 6 ohms here. The EMF is equal to 18 volts. The next thing that we want to do is to find the current through each resistor. Now, in order to do that, we're going to do something pretty similar to what we did with the capacitor problems like this, which is that we're going to start from the right-hand side, the finished kind of picture, and we'll just slowly work our way back. Okay, so in this picture here, we know that there's going to be some current that's going to be flowing from the positive side of the battery. We can call it I. And I would say that this current I should be equal to the EMF of the battery divided by the resistance. Remember, EMF is just, it's really just another word for voltage, but it's a more specific thing that means it's related to the source itself and how much electromotive force it's placing within the circuit. Okay, so if we take 18 volts and we divide by 6 ohms, it's a tough calculation, but I think we get 3 amps. So that's going to be the current that's flowing through the system here. We then have to look back to our picture that came before and say, well, if that current was flowing through this combination of the 4 ohm and the 2 ohm resistor here, then what would the current flowing through the 4 ohm resistor be?
There's 3.
It's also 3. Because if we say that the current coming in here is 3 amps, then the current going out the other side is 3 amps, then the current flowing through each resistor should also be 3 amps. So the current through this one is going to be 3 amps, the current through this one's 3 amps. And now we basically solved that the current through the 4 ohm resistor is 3 amps, because that's this one right here. For the 2 ohm resistor, though, because these two are in parallel, we can't just say that there's going to be 3 amps flowing through this one and 3 amps flowing through this one. It's going to split. Okay? And more current should be flowing through the 3 ohm resistor. My guess would be that you're going to have 2 amps flowing through here and 1 amp flowing through here because this is half as big, right? So in order to figure that out, what's up?
That's true. Yeah, true.
Okay, so in order to actually figure out what the current flowing through here, though, if the numbers were more complicated and you couldn't just do it in your head, what we would do is we would say, well, delta V is equal to I times R, so the potential difference between these 2 points in our circuit here should be equal to the current flowing through those points, which is 3 amps, multiplied by 2 ohms, so it's going to be 3 times 2. I'll still write it out. So 3 amps times 2 ohms is going to give us 6 volts, and just to check, that's less than this voltage, which is a good thing. If we wanted to continue the same calculation over here, what would the potential difference between or across the 4 ohm resistor be?
Be 12.
And then we can just check 12 plus 6, that adds to 18. Looks like we're doing okay. Now that we know that the potential difference across the 2 ohm resistor is 6 volts, you have to have the same potential difference drop across both of these here. So for both the 6 ohm and the 3 ohm, we're going to have delta V is equal to 6 volts. That means if I want to find the current flowing through the 6 ohm resistor, then all I have to do is to take that 6 volts and divide by the resistance, which is 6 ohms, and I get 1 amp. That was exactly what I said we'd probably get. And then for the 3 ohm resistor, if I want to find the current flowing through that one, then I'm going to get the same delta V, 6 volts. And again, same potential difference because these are in parallel, right? They have to have the same. So if I told you over here that between points, see there's C and B over here, between points C and B, that the potential difference was 6 volts, well, it has to be 6 volts here too. All right, for 3, you take 6 volts, you divide by 3 ohms, and we get 2 amps, which is exactly what we guessed it would be. So those are our answers. 3 amps, 1 amp, 2 amps, and this was the equivalent resistance. And that's it. Anyone have any questions? If you were already able to do the homework from 2 weeks ago with all the capacitors, solving problems like this isn't really any different at all. Okay, now, not all circuits are simple enough that we can use this process. this chapter is kind of weird because it starts off by teaching you about the way you combine the way you combine resistors, and almost immediately we talk about problems where you can't do this. That being said, this can be useful in certain problems. Sometimes you're going to have systems where you're going to look at stuff like this and you're going to want to simplify it. But the real question becomes, what happens when I drop a battery in here? So that I have like a battery up here, but I also have a battery right here, or a voltage source. That's what we want to understand next. And in order to do that, we're going to use what are called Kirchhoff's rules. Kirchhoff's rules? I think it's rules, not laws. I don't know. So, Kirchhoff's rules are going to be the loop rule and the junction rule. And we've got some things that I copied over here for this. Okay, so let me just state what the rules are first, and then we'll look at this picture, because this is a little much. Okay, so the first rule we call the junction rule. The junction rule basically states what happens. We actually used it in the previous problem. The junction rule states what happens when I have a scenario like this. Say that I have a circuit, and within my circuit I have a position where the current flowing in one position is, or in one branch of the circuit is I1, but then there's a junction where the current splits, let's say, into 3 parts. And I call the current flowing in the top part I2, the current flowing in the middle part I3, and the current flowing here to be I4. The junction rule is really just a restatement of conservation of charge or conservation of current at a node like this, or a junction. A junction is any time when you have a split in your circuit, it needs to have at least 3. So I could get rid of I4 here, it'd be I1, I2, and I3, but you can't just have 2. And what the junction rule states is that around that point, that if I define incoming current to be positive and outgoing current to be negative, that if I sum up all of the currents, they should sum to 0. And the caveat here is that we're going to say that current flowing into the node, or incoming current, we're going to make that positive, and then current that flows out of the node, we're going to make negative. This, we could reverse these, it wouldn't really matter, because you're summing to 0. Okay, you just need to create a convention for yourself. So I'm going to call incoming current positive and outgoing current negative. And according to that, then the junction rule says that if you sum up all these currents, they should sum to 0. So in the picture that I have drawn right here, what that would mean is I1, which goes into the junction. Again, this is what we call a junction, or a node or something, whatever you want to call it. I1 is coming in, so that's positive. I2, I3, and I4 are all going out, so we're going to subtract all 3 of those. So I2 minus I3 minus I4. These are all going to sum to 0. And that's the junction rule. It's really simple. Of the 2 rules, this is definitely the easiest. Does anyone have any questions? Let's look at these 2 circuits right here. So there's a lot of lines drawn in here, and I know that's confusing, but what we have in this circuit is we have an EMF source E1, another EMF source E2. Again, these are just batteries or power sources. This EMF source has an internal resistance little r1, this one has an internal resistance little r2, and they're both connected up to a resistor that's just called R here. Within this circuit, and note that this says the caption here is that 2 networks that cannot be reduced to simple series parallel combinations of resistors. So we can't reduce down this circuit just using parallel and series. Is it clear why we can't? It's mostly because of this battery right here. If you take out this battery, then, well, even then we couldn't do it because there's this resistor that's in this branch of the circuit that only contains the battery. So, that's not true. You could do it. If we just got rid of this battery, we could do it. Because then we could combine R2 and R with a parallel combination, and then little R1 would be in series with those. So, if you just removed one or the other battery, it would be possible to actually turn this into just a simple circuit with just one equivalent resistor. But the fact that there's two battery sources and two batteries in here means that we can't do that. Now, where are the junctions? Well, they've kind of indicated for you here that this is a junction, and this is a junction, because you have a branch, another branch, another branch. That's 3, right? Same thing over here. There's a branch here, there's a branch here, there's a branch here. That's 3. You need to have at least 3. But the corners are not junctions. Okay? So a corner is just a place where the wire has been bent into a corner. And it just as easily could have been bent into like a curved shape. So the current flowing within this entire region out here is going to be the same. You're going to get a different current in here, and you're going to get a different current flowing on the left side over here. Okay? It's only the place where you have at least 3 wires that meet that you're going to get a junction. You could have more. You could have 4 or 5, whatever. Okay. Does that make sense?
Mm-hmm. Mm-hmm.
Okay, on this circuit right here, can you all tell me? I guess the easier question to ask is, of the 6 letters that are here, A, B, C, D, E, F, can you type in chat, which of these are not junctions in the lower circuit? And can you read that? Do I need to make it a little bigger? So we've got A, B, C, D, E, F. Which ones are not junctions? E and F. That's right. That's right. Maybe that's kind of easy, I don't know, but it's still worthwhile to ask you. And these are not junctions because there's really just there's one wire that goes into F and out of F. But when you look at point A, you've got one wire here, and it splits in 2. I believe this type of arrangement is something called a Wheatstone bridge. I think that's what they call this. And we would have done a lab that used something like this, yeah. Anyway, so that's a junction, right? All right, now let's talk about the other Kirchhoff rule. So you got the junction rule, and the other one is the loop rule. This one is a little bit more complicated. These have names that I've seen in other textbooks. Like, I can't remember what they are, but I think this one is sometimes shortened to be KVL or something like that. I should write this down because I can't remember what it is. Like Kirchhoff voltage loop or something like that. I can't remember what the way that they... But you'll see other names for these things. They mean the same thing. But, yeah. Okay, so the loop rule states that if I can draw a closed loop within my circuit, that around any closed loop, any loop that you choose to draw within your circuit, and I'll just, you can kind of see what loops are if you look at these pictures here, but I'll define more clearly what I mean by a loop. Around any closed loop basically means you start from one point in a circuit, you go around in a circle. We know that if I sum up all of the voltage drops, that these should sum to 0. That is the loop rule. Now, the way in which we actually use the loop rule requires some conventions that I'm going to state for you now, but let's talk about what a loop is first. All right. So a loop means you pick some point, let's say point A right here, and you basically just imagine that you're traveling around this loop. Okay? As if you were like going on a bike ride around a neighborhood. You start at one point, and you got to make sure you finish at that same point. You got to go all the way around. You don't want to go through half. So you need to have a closed loop. On this picture, there's drawn 3 loops, okay? Loop 1 starts off, let's say, at point A, and it goes in this direction, so it goes all the way around the circuit and back to the same point. loop 2 starts, let's say, like right here, and it goes in a circle like this, also going, what is that, counterclockwise. And loop 3 goes in a circle around like this. And what you need to do is, for any of those loops, you basically have to write down an equation. For every single element that you get within the loop, whether it be a resistor or an EMF source, there's going to be something that you're going to write down. Just as an example of how you're going to write it down, I'm just going to show you an example first before I tell you the rules, okay? And I'll tell you how I knew the rules, I guess. So let's do, I guess loop 1 is probably the simplest. It's really not, though. All right. Does the direction that the loop goes related to the direction of the current? Kind of. They interact with each other, but they're not related to each other, if that makes sense to how. Okay, so in order to even use the loop rule, we have to actually add some extra things to our picture. Usually what happens is in order to use Kirchhoff's rules, you're going to draw the direction of your currents. Okay? Drawing at least one current for every branch of your circuit. So what I'm going to do here is, since this source is called E1, what I'm going to do is I'm going to say that the current flowing in this section is going to be I sub 1, okay? And keep in mind that that same current doesn't just flow up here, it also flows in the bottom down here, and it flows straight through both of these. So I don't know where to put it, but this same current I1 flows all throughout the branch from B up to A, okay? That current I1, okay? And then I'm going to say the current flowing between B and A, I'm going to name that one to be I2. And again, it's the same current all the way through the branch from B to A, so I'm going to call that one I2. You might want to call it IBA or something if you really wanted to, but I think that's kind of excessive. And then finally, we're going to have current that's flowing through this resistor R. Now, it's important to understand that even though I drew this current I1 flowing this way, and I drew this current I2 flowing this way, I don't really know if that's what the direction the current's flowing, because I don't know how big these batteries are. If this battery, for example, was 10 volts, and this battery was 1 volt, then I'd be pretty confident that the directions I've drawn here are correct. But if the battery on the right, epsilon 2, is like 100 volts, and this battery was like 1 volt, well, if I have a battery that's 100 volts driving current through a circuit, and I have another battery that's 1 volt driving current through a circuit, would you all agree that the 100 volt battery is going to kind of win? And it's going to have more power coming out of it?
Mm-hmm, mm-hmm.
So as a result, this would kind of win, and I would probably guess that the current I1 would actually flow the other direction due to the influence of this power source here. Now, it's important for you to understand that line of logic that I just used there, where I tried to figure out what direction the currents are going, is completely a waste of time. You do not have to figure out what direction the currents flow in these circuits. The math will work it all out for you. So, regardless of what you do, you just need to pick. I'm going to keep repeating this as we do problems, but you literally, I picked I1 going this way, and I picked I2 going this way. I have no reason to know that those are correct, okay? So, yeah. That being said, for the current in the branch out here, what direction do you want to draw it? Do you want to draw it to the right on the top side, or do you want to draw it to the left? What do you all want to do? It makes no difference.
Do right.
Okay, we'll make the current go to the right. I'm going to call it, since this is I1 and I2, we'll call this one I3. And here, just as an exercise, can you all tell me, what would the junction rule say for I1? Or, sorry, for point A. What would the junction rule say for A, according to our definition up here? Can anyone write down in chat what it would be, or just cue your mic and say it's fine?
It'd be I1 plus I2 minus I3 equals 0.
Exactly. Can everyone see that?
Yep.
That's really simple, right? Okay. So if you're going to get any part of this right, you better get the junction rule right, because it's definitely the easiest part. Okay, so can you also see that if I made this negative I1, negative I2, and positive I3, that it wouldn't matter? You just need to be consistent, okay? You don't need to memorize this. You don't need to memorize the incoming current's positive and outgoing current's negative. You just need to memorize that they're not all positive, right? Something has to be negative when you have a junction. Well, they could all be positive, actually. If I3 pointed to the left, it would be I1 plus I2 plus I3, right? Would you all agree with that? If this I3 was going in, then they would all be the same sign. Okay, so I guess they could all be positive. But, yeah, anyway. All right, so, and that would be totally fine. There'd be nothing wrong with that. Okay, so the loop rule says around any closed loop, the sum of the voltage drops is going to have to be equal to 0. So how do we actually do that? I'm going to write what it is down. We're going to start with loop 2, and then I'm going to tell you the rules, and I'm going to have you all do loop 1 and loop 3, okay? All right, loop 2 is drawn. I really hate the way that it's drawn, unfortunately, but it's already drawn in there for us. We're going to do more problems. We'll have plenty of time to... Hey, what time is it? No, we're doing good. I did record this, didn't I? Yeah. Okay. All right. So around loop 1, this is what summing the voltage drops is going to be. Now, this is annoying because loop 2, sorry, I'm talking about loop 2. The current's opposite to the direction we're going, okay? So what I'm going to do is I'm going to start, you got to pick a starting point. So I'm going to start here. We're going in this direction. We're kind of going against the current, right? I'm going against the current. So what I'm going to write down for this first resistor here is positive I1 multiplied by little r1. And why is it positive? Well, it's positive because you're effectively going uphill. All right? You're effectively going uphill. We get to the battery here, and as we go across the battery, because the positive side is here and the negative side's here, we're actually going to get a negative E1. These positive and negatives, I'm going to explain where they come from, but I just want to give you an example of one first. We then need to go around to here. Am I going the right way? Yeah, loop's going this way, right? The next thing that we encounter in our circuit is E2. Now, the direction of the loop we're traveling is up now, and we're going from the negative side of the battery to the positive side of the battery. We're going from the lower voltage side to the higher voltage side, which means we're going to put plus E2. Okay, because when I have a battery in a circuit like this, and I tell you, for example, that it has an EMF of, let's say, 9 volts, what that means is that the bottom side down here is probably at like 0 volts, while the top side up here is at 9 volts. So if I traverse my loop in that direction, I'm going from the 0 side to the 9 side, I'm kind of gaining potential difference. Delta V is positive, okay? Change in voltage would be final minus initial, 9 minus 0. So plus E2 is what I'm going to put there, because the direction of the loop corresponds to the going from negative to positive. Now, when I get to my resistor right here, R2, that has a current I2 flowing through it, I'm going to write minus I2 times R2. And all of this has to add to 0, because now we're back to the same point we started, okay? So within this one loop, we've actually seen all of the, right? All the possible combinations, actually, that you can possibly get. Notice that for the first resistor here, I put a plus sign, but for the second resistor, I put a negative sign. The reason why I did that was because we were going against the current when we went through R1, which means that since you're going against current flows in the direction of decreasing voltage. So when we go against the current, we're going to a higher point. It's like going uphill. Going from this point in the circuit to this point in the circuit is like going up a hill. And if you want to replace the current with like water flowing down a hill, it's perfectly acceptable here. And you're basically going uphill to get from this point to this point because you're flowing against the current. You're going from a lower potential to a higher, from a higher potential to a lower potential. For example, this side of the resistor could be at 8 volts and this side of the resistor could be at 0 volts. So you're doing basically final 0 minus 8, which would be negative. Okay? That's where that negative sign... Wait. Did I just confuse everybody? I had it right the first time. Ooh, these negative signs can be confusing. So if this side was 8 volts, for example, and this side was 0 volts, then yeah, it'd be positive, because you're going to the higher potential on your resistor here. Okay. When we get to our battery, we said that you get a minus sign, and that's because we're flowing into the positive side and out the negative side. And that would be like going to a position where, like, let's say this is 8 volts over here, but this is 0 volts over here. You're going to a place where the final is lower than the initial, so the change is 0 minus 8. Keep going over here, and it's exactly the opposite situation. Once we get to the branch right here, the direction that we're traveling on the loop is the same as the current direction. That doesn't actually matter for the battery. The battery, we go across it, we're going from negative to positive, we're going to a higher potential, which means we're going to get a positive E2, and then as we go across the resistor, we're going to a lower potential, because we're going in the same direction as the current, so we get a negative right there. Okay, so I tried to explain where those numbers came from, and I don't know if anybody followed any of what I just said, but I'm going to keep repeating some of those ideas as we go through this. This is a set of all of the conventions that you need to know to do this. Okay, there are basically 4 possibilities. You have sign conventions for EMFs. Okay, the line that's drawn on top right here is a line that represents the direction of the loop. So when it says travel, it's like the loop. You're traveling around your loop right here. So when you go from negative to positive, like this, you get a positive E. That's what happened in our loop here, because we were going up. This is the negative side, this is the positive side, so we got a positive E2. If your direction of travel is to go from the positive side of the battery to the negative side of the battery, you're going to get negative E. See? Positive E, negative E, just depending on which way you're going. And again, if this doesn't make sense, and you want to have some kind of way of remembering it, remember that replace this thing with a battery. When you go buy batteries, you're buying something that has, like, let's say, a potential difference of 9 volts. If I have a potential difference of 9 volts, what that means is that on the right-hand side of the battery, coming out the positive side, I have like 9 volts of energy, effectively, or energy per charge. And on the left side, we could just say, well, if it's a 9-volt battery, if this is 9 volts, then this side has to be 0 volts. Okay? And then if you put it this way, since what we're calculating here is delta V, right? This is what we're doing. Delta V would be V final minus V initial, which in this case would be 9 minus 0. And then so it's positive 9, right? That's positive 9 volts, or positive E. If your direction of travel is the other direction, then again you say, okay, well, it's the positive side of the battery, so this is going to be my 9 volt side, this is going to be my 0 volt side. So again, delta V is going to be V final minus V initial. So 0 minus 9, you get delta V is equal to negative 9 volts, or, negative E. Okay, does that make sense?
Yeah.
Okay, hopefully that's something you can remember. Even if you don't remember, you can just memorize this, right? But I think it helps to have some idea, like, this is physics, right? So we kind of understand some of the, like, method to the madness. There's a reason why we call one of them positive, and there's a reason why we call one of them negative. It's because that's what the potential difference would look like. If we were to literally measure using a voltmeter, and we measured it so that we put, for example, I think it would be like the negative lead of the voltmeter here and the positive lead of the voltmeter here, we would get a readout of 9 volts. But if we reversed the leads, we would get a readout of negative 9 volts. Okay, so it's consistent with measurements too. This isn't just, we're not just making this kind of stuff up. All right. Now, resistors are a little trickier because you also need to include the current, okay? So the sign convention for resistors state that when you travel opposite to the direction of the current, then you're going to get positive IR. And when you travel in the same direction as the current, you're going to get negative IR. That's why on this picture over here, when we did loop 2, okay, we were going opposite to the direction of the current here. We were going from the top to the bottom, right? We're going around the loop in this direction, counterclockwise. So when we traverse the loop opposite to the direction of the current, you get a positive IR. When you're in the same direction as the current, you get a negative IR, right? So the loop and the current are opposite, it's positive. If they're in the same direction, it's negative. And again, if you want to remember why this works out the way that it does, I think the analogy of a hill is really helpful, because when you're flowing downstream or downhill, you're going to a place of lower potential energy, right? Like, say we got a hill, and it has an elevation of 10 meters on top and 0 meters on the bottom, okay? If I go up the hill in this direction, what happens to the change of potential energy, delta U? Is it positive or negative?
Positive.
Positive, right? And if I travel down in this direction, I'm going to get delta U as negative, right? Change of potential energy is less than 0 because you're going downhill. It's exactly the same thing here. If you go in the same direction as current flow, or gravity flow in this case, then you're going to get from this one negative IR. And if you go opposite, you're kind of going uphill. This is like this. This is like going upstream. You get positive IR. And those are the sign conventions. I think this is pretty much a good place to stop. So we're gonna do one thing and then we'll stop. Does anyone have any questions? All right. If you don't have questions now, as soon as you start trying to do this, you will have questions. So that's what I want you to do now. I want you to take this picture that we've drawn over here, using the same names that I've used for the current. I just have a question. Would you mind if I got rid of some of these currents on this picture? Like if I got rid of this one and this one? Hopefully now that you understand that the current flowing all throughout here is... Okay. So let's get rid of that one. Let's get rid of that one. And let's get rid of this one. And... one of these has to go, so we'll get rid of this one. So now we just have... So hopefully you'll understand from now on that when I write I1 right here, it goes all the way to the junctions. And when I write I3 right here, it goes all the way to the junctions. All around there. And I2 is just contained within here. So what I want you all to do now is to look at... I guess loop 1 is probably the easiest. I want you to write down Kirchhoff's loop rule for loop 1. And what I'd like for you to do first is to just try to write it down on a piece of paper or a tablet or whatever you're using. Just write down what Kirchhoff's loop rule would be for loop 1. Just give it a shot. If you can't do it, it's fine. We're going to do a bunch of examples. If you finish that one and you're pretty confident, you can write down what it is for loop 3. I basically want you all to try to do both of them before we go on break. I'll give you a minute or two. Don't worry about getting it wrong. Just try to do it. Just try to... Really what I want you to do is just to try to understand these sign conventions. Let's see. So this was loop 2 that we did, right? Okay, was that enough time? What do y'all get for loop 1?
I got I1 R1 minus E1 plus I3 R equals 0.
Is it, you say minus E1?
Mm-hmm. And then plus I3 R equals 0.
Okay, it sounds like a lot of people are getting the same thing. Let's just go through why that's the case. Loop run goes counterclockwise as well. We look at this piece right here. As you go down, I1 is flowing up. So we have the situation where the direction of travel and the current are opposite. That means we write down plus IR right here, just like you all did. And then again, we go across the battery. We're going from, it's this picture right here, from plus to minus. I really do like the way the book does this. I kind of wish they kept the travel direction the same and they flip the battery direction, but it doesn't make any difference. So if you're going to the left and you have a positive on this side and negative on this side, that gives you a negative E1, and then we get around to here, current's flowing against us, so when we go up, we're going this way with the loop, but the current's against us, you put a plus. Great work. And then to just finish off loop 3, we're going this way, right? You should have gotten something like, what do we get for the first term here for loop 3? We're going
Positive I2 R2.
Yep, plus I to little r2, and then you go across the EMF source plus to minus, so we're going to get, what, negative or positive?
Negative.
Nope, negative E1, or E2, sorry, because again we're doing, it's this one, travel direction from plus to minus. And then finally, I'm probably blocking at this point, no, not quite. Finally, let's see, what, loop 3, so we went around this way, still going against the grain with I3, so it's going to be plus I3. It's off screen, I'll move it, times big R. There we go, that's loop 3. And now what you can do to kind of like drive all this home is with these equations, 1, 2, 3 equations, plus this one, a fourth equation, you can solve for all the currents. So if, for example, you were given each of the EMFs, like if EMF 1 was 9 volts and EMF 2 is 18 volts, and I told you the resistance here was 10 ohms, 5 ohms, and 25 ohms, given that set of information, you could solve for the 3 unknown currents. In fact, you have one extra equation, because you have 4 equations, and you really probably would only have 3 unknowns. Some problems, they're going to give you one of the currents, and it'll have you solve for a battery, but at the end of the day, yeah. So you'll see a lot of problems like this in your homework for this chapter. They are, I really think they're quite easy, and we're going to do, I think, 3 of them when we come back from break, and then after that we'll talk about RC circuits. So that's the plan for today. And does anyone have any questions before we take a break? Is it easier if we make all loops go in the same direction when we're doing homework? Well, it's really up to you to how. You just get to choose. It's completely your choice. Because if we had drawn loop 1, for example, to go clockwise, all that would happen, maybe you can tell me, what would happen if I just switched the direction of the loop?
Just be multiplied by -1.
Yeah, exactly. If I just switch the direction of the loop, this would be negative, this would be positive, and this would be negative. So to how it makes no difference at all. Just choose whatever direction you want. And to go back to one of the things I said earlier, I'm going to need to keep repeating this because people always forget. Remember at the very beginning of this? And maybe you don't remember because we're doing a lot of stuff here, but I picked directions for each of these currents, right? It also doesn't make any difference what direction you pick, because the answers will either be positive or negative, and it makes no difference what direction you pick. So you're free to choose the loop direction, and you're free to choose the current direction, and then as long as you write down all the equations correctly, it'll all work out. And in addition, because sometimes this is going to involve like 3 equations with 3 unknowns or 4 equations with 4 unknowns, and solving such systems can be kind of complicated, you all probably learned in one of your algebra classes, or in your, if you took linear algebra, you certainly probably did it. But there's a method that you can use to solve types of equations like this using matrices, using something called reduced row echelon form. So that's the other thing we're going to do today is we'll talk about how you can solve groups of equations using like your TI, like TI 83, 84, or 82, and also how you can find a place on the internet to do the same thing. All right, let's take a break though. We'll break until 3:12.